In 1800, Napoleon was preparing to invade England on behalf of the fledgling French government. His orders at that time were to head straight to England and take the rival country by storm. But a crafty Napoleon had a better idea, and the chops to pursue it in defiance of his own country's leaders. Napoleon instead decided to first cut the trade routes used to supply England by moving his army into Egypt. It was a bold strategy from a militaristic standpoint, but as it also turns out, his decision might have ultimately had a greater impact on the scientific world than it ever had on the map. You see, Napoleon took with him a band of scientists, and some of the discoveries that these scientists made were nothing short of spectacular. The most notable of these is, of course, the legendary Rosetta Stone that unlocked the ancient languages used in texts from biblical times and beyond. But another great breakthrough began there as well. One that isn't as celebrated, but has no less of an impact on how we think about the world's form and function. A well-established and revered French scientist by the name of Claude Louis Berthollet was along for the expedition. A contemporary of some of the greats like Lavoisier, he was astute at observing the world around him and inferring what he could about the behavior of matter. One day, on the shores of Lake Natron, in what is modern-day Tanzania, he noticed something. As the lake waters had evaporated over years and years, a thick crust of material had formed around them. He easily identified this material as sodium carbonate, a chemical known in ancient times as natron and the namesake of the lake. The nature of the material wasn't what inspired him, though. What Berthollet took notice of was that it seemed to be forming as sodium chloride reacted with calcium carbonate in the limestone on its shores. Now, what made this so remarkable to him was this. He knew this reaction very well, but had always encountered it in the reverse in his laboratories. In all of his studies on these materials, he had created sodium chloride and calcium carbonate from natron, but not the other way around. Now, this seemingly casual observation turned out to be anything but. It was the seminal moment in which one of the great founding fathers of the chemical sciences asked the question, must reactions always happen in the same direction? Or can they be reversed? Clearly, from his observations in northern Africa, he concluded that they could. This experience changed his way of thinking about chemical reactions in very much the same way that I'm going to attempt to change yours today. Today we ask the same question that Berthollet did in 1803. What happens when reactions can be reversed? You see, we just spent 4 lectures considering reactions as though they were unidirectional, only moving from reactants to products in an irreversible process. But, as Berthollet's story makes all too clear, this is, quite literally, only half of the story. In other words, we never ask the question, if A can turn into B, can't B possibly turn back into A in a reversal of the process? And sometimes this is exactly what can happen. Not only that, but both happen simultaneously. Let's try to get our heads wrapped around this using an example more familiar than chemical reactions. Have you ever played a game of dodgeball? It's a great game, isn't it? 6 balls flying back and forth from one side of the court to the other amid the chaos of jumping, running, and twisting humanity. Now, most of us probably have memories of this game from our childhood. In this simple game, the dodgeballs undergo a change. They interconvert, if you will, from being on one side of the court to the other. And of course, when one team throws a ball into another's court, the process is pretty quickly reversed, or else that team isn't going to fare so well in the game. So the process of throwing dodgeballs constitutes a reversible process. Once the game gets going, if our teams are evenly matched, at any given time, we're likely to find about 3 dodgeballs on either side of the court. The total amount of balls in each state is unchanging. Yet, as the game progresses, dodgeballs are flying back and forth repeatedly from one side to the other. This is an equilibrium. It's a dynamic state in which change is still taking place, forward and backward, but at identical rates. One very common misconception that we need to break right away is that equilibrium means there are equal amounts of starting material and product. This is not always true. In fact, it's very rarely true. Let's go back to our dodgeball game once more. If one side's players can throw the balls back twice as fast as the other, during the game we instead see 4 balls on one side of the slow team, right? And 2 on the side of the fast team. But once that steady state is reached, the rates are equal. The population on both sides stays constant. So it should be evident now that it's possible for populations of chemical reactants and products to be different even when the forward and reverse rates are the same. Now, this is both an exciting and disconcerting realization. Exciting because that complexity means there's much to explore, but maybe a little disconcerting because such complexity can often be tough to model and predict. Well, let me put your concerns to rest right now. It turns out that systems at or on their way to establishing equilibrium actually follow a remarkably simple mathematical model. And by the end of this lecture, we'll be well on our way to understanding the equations that govern this critical chemical process. Before we begin our investigation of modeling chemical equilibria, we first have to define 2 very important kinds of chemical equilibria. Chemical equilibria fall into 2 broad general classes. The first of these classes is homogeneous equilibria. In homogeneous equilibria, all of the reactants and products of the process are of the same phase. For example, the synthesis of gas phase methanol from the gases carbon monoxide and hydrogen would fall into this class since all 3 species, the 2 reactants and the product, are all in the gas phase. The second class is heterogeneous equilibria. In heterogeneous equilibria, reactants and products of differing phases are being interconverted. For example, the combustion of carbon using oxygen, a reaction going on in power plants and barbecue grills all around the world right now. That's a heterogeneous reaction. Here, solid carbon reacts with gaseous oxygen to form gaseous carbon dioxide. We'll give all these types of chemical equilibria their due attention as we go along. But for this lecture, we're going to simplify by focusing on homogeneous equilibria in the gas phase. Once we've learned the tools necessary to investigate, model, and even manipulate this class of equilibrium, we'll come back to the others and see how they fit in as well. So we've defined equilibrium as a state in which forward and reverse reaction rates are equal to one another. This is good news for us because it means that there must be some connection between rate laws and how systems behave at equilibrium. So our goal for today is to consider reactions not just in a unidirectional sense, but in the sense that they can sometimes go backwards. Now here's an example. A reaction of NO2 to form N2O4. We've seen this reaction quite a few times already, and we've always presumed that whichever direction we wrote the reaction in was the only direction it could go, which is to say that 2 NO2s can form N2O4, but don't go back the other direction. Now, this reaction would be governed by a rate law that would look like this. K for that forward reaction times the concentration of NO2 squared, assuming, of course, that this is an elementary reaction. But now we need to start considering something else. The possibility that this reaction could go in reverse, that N2O4 may decompose and form NO2 molecules as well. Now, if that were to happen, we would have a rate law that would look something like this. A different K value, one for the reverse reaction, times the concentration of N2O4, the product as I've written my reaction. Now, this is the central idea around equilibrium, that reactions can go forward and backwards and establish a situation in which rates are equal. Now let's think about that for a moment here. If rates must be equal in order for equilibrium to have been established, that means that in this case, the forward rate law expression must be equal to the reverse rate law expression. So I have an equality to work with. And doing just a little bit of rearranging here, dividing through by the reverse rate constant, and again by the concentration of NO2 squared, gives me a new relationship, where K for the forward reaction divided by K for the reverse reaction is equal to the concentration of products raised to an exponent equal to their coefficient, divided by the concentration of starting material raised to a power of their coefficient. This relationship, little k forward over little k reversed, is what we call big K, or the equilibrium constant for a reaction. And this is going to be the central focus of this lecture. So let's think about how to derive the equilibrium constant one more time in a simpler way now that we really understand the inner workings. Here's a reaction that's also in equilibrium. This is 3 moles of O2 gas in equilibrium with 2 moles of ozone gas. Now, we don't know for sure that that is going to be the equilibrium concentrations, but that is the stoichiometry of the reaction. That means that oxygen can react to form ozone, of course. But we now know that we have to consider that ozone can also react with itself to form oxygen. The process can be reversed. And the equilibrium is governed by the equilibrium constant, in which we have the products raised to their coefficients over the reactants raised to their coefficients. In this very simple case here, we have a situation where that is ozone squared divided by O2 cubed. Ozone in the numerator because it is a product, raised to the second power because of its coefficient, divided by oxygen in the denominator because it's a reactant, and raised to a power of 3 because of its coefficient. So as I've written this reaction, this would be the expression for the equilibrium constant. So now that we understand exactly what an equilibrium constant is, let's think a little bit about how we get those numbers. Let's take a look at a problem here. Samples of hydrogen and iodine are mixed together in a 1-liter vessel at 430 degrees centigrade, and equilibrium is established. And once equilibrium is established, we have 2.5 moles of HI, 0.25 moles of H2, and 0.5 moles of I2 gas in that 1-liter container. So this is convenient because this means that these numbers are not only the number of moles, but also the molarity, which we need for our equilibrium constant. So what is the equilibrium constant? Not just the expression, but the actual number itself for this system. Well, here's the reaction that we're talking about. H2 gas plus I2 gas forms 2 moles of HI gas. So let's first get the equilibrium constant expression, then use our data to get the equilibrium constant itself. In this case, KEQ is going to be equal to the concentration of the HI product squared, because of its coefficient, divided by the concentration of the starting material H2, divided by the concentration of the starting material I2. In this case, both raised to a power of 1, which is understood, so we typically don't write that in. But we're going to take the next step now. Use the information given from our experiment to get an actual number to assign to the equilibrium constant. So I'm going to take my 2.5 moles of HI in 1 liter, place that into its location. We'll take our H2 concentration, and we'll take our I2 concentration, and insert them into the equilibrium constant expression. The math here gives us the number 50. At 430 degrees centigrade, for the reaction between H2 and I2 to form HI, this equilibrium constant will always hold. Any system of these 3 gases at equilibrium at this temperature will have to conform to this number. So now that we have derived the equilibrium constant for our reaction, let's put it to use. Let's use it in a manner that will allow us to predict what will happen at equilibrium rather than just observe what's happening at equilibrium. Here we are again, looking at the same reaction, H2 and I2 to form HI at 430 degrees centigrade. But we have a new question. The new question is how much HI gas will form when I charge that vessel with 2 moles of hydrogen and 2 moles of iodine. Again, 1 liter, which is convenient because it means that moles and molarity are equal. To do this, I'm going to use a little mnemonic called a Rice table. That stands for reaction, and then initial change, and equilibrium concentrations. So I have to get all of this information in terms of a single variable before I can use the equilibrium constant expression to determine what will happen in my reaction. So let's get down to business here. Let's get our Rice table started. Of course, the first thing we need to do is write our reaction. H2 plus I2 forms 2 moles of HI. That leaves me with 9 entries that have to be completed before I can start working with the equilibrium constant itself. The initial concentrations of all, the change of all, and the equilibrium concentrations of all of them. Let's see what we can do here. We're starting with 2 moles of hydrogen in a liter. We've got that number. We're also starting with 2 moles of iodine in the liter vessel. We've got that number as well. Now, for our starting concentration of HI, we're assuming that there's none there, that when we first mix H2 and I2, we can somehow hold back time and freeze it before any reaction takes place. That being said, we would assume that the concentration of HI originally is 0. But as soon as we unfreeze time and let that reaction go, what happens? Well, we experience a change in concentrations, of course. We'll lose a certain amount of hydrogen gas, but we don't know exactly how much. So we're going to call that minus X, where X is the number of moles of H2 we lose. Well, what does that mean about I2? Well, because of the reaction stoichiometry, I know that I2 is going to change by the exact same amount. Has to, right? And I can also predict how much HI will form in terms of that variable X, because the reaction stoichiometry is 2 to 1. So however many moles of H2 are lost in the route to equilibrium, 2 times as much will be obtained of hydrogen iodide. Now our equilibrium concentrations. These aren't so tough. All we have to do is take our initial amount and apply the modification, apply the change that we previously determined. So hydrogen will be 2 minus X. Iodine, also 2 minus X. And HI, 0 plus 2X, which for simplicity's sake, I'm just going to drop the 0 there and call this 2X. So my Rice table has allowed me to get a single unknown inserted for all of these numbers here. Anything I don't know now is in terms of X. And that means all I have to do is come up with one valid equation to solve for that one unknown, and I'll be on my way to completing my problem. So let's finish this one up here. Our reaction again is H2 and I2 to form 2HI. And here are our equilibrium concentrations that we determined previously using our Rice table. Let's put these into the equilibrium constant expression, which we now know is equal to 50 because of our earlier work. HI squared over H2 times I2. In terms of X is 2.0 minus X for H2, 2.0 minus X for I2, and 2X for HI. These are all equilibrium concentrations, and so they belong here in the equilibrium constant expression. Now we can solve for X. In this case, it's actually rather simple, because we can take the square root of both sides of the equation to drastically simplify things and solve for X right away. If that weren't possible, we'd be looking at a quadratic equation solution. So if you're going to solve more complex problems, you'll want to be sure that you're very studied in the quadratic equation. But again, we lucked out here. We can use a square root of this equation to get our answer much faster. Here, X is equal to 1.6 moles, or 1.6 molar because we're in a 1-liter vessel. Are we done? Have we answered the question? Well, the question is how much HI gas will be present. But X does not equal the amount of HI gas. It's my tool to get the answer, but it's not the answer itself. Remember that HI is 2X, so I have to account for that in my final answer. It's actually 3.2 moles of HI gas that I expect to be present at equilibrium. So our predetermined equilibrium constant allowed us to sit at our desk and answer questions about experiments that we haven't even run yet. Just think of all the time and cost and trouble that we can save, all because we understand how the equilibrium constant works. Now, because it's derived from a written equilibrium reaction, the value of K for any reaction can depend on certain choices about how we wrote our reaction. For example, I can write my reaction as 1/2 H2 plus 1/2 I2 is in equilibrium with 1 mole of HI. Now, if I do that and use this reaction instead to determine KEQ, I have to realize that the exponents in KEQ will be half those of my previously used expression. This means that if I choose to write my reaction this way, effectively halving the reaction, I would have to use the square root of the value K that I determined previously. Also, consider that if I reverse the reaction, making the products reactants and vice versa, forming 1 mole of H2 and 1 mole of I2 from 2 moles of HI, the rate constant becomes inverted. I have to compensate for that by using the reciprocal of KEQ as I calculated it previously, 1/50th, or 1/50. So it's critical to carefully consider how a reaction is written in your problem and be sure that it's consistent with the KEQ value that you are using to solve that problem. There's one more tool that we need to discuss today. And consider this. When a non-equilibrium mixture of reagents is created, we sometimes want to know which direction that equilibrium will shift without necessarily needing to know exactly how much of each component will be consumed or produced. When this is the case, we can use a mathematical tool called a reaction quotient to get a quick read on roughly how far a mixture is from equilibrium and which way it will shift to get there. This is helpful when deciding how to set up the C row of my rice table, allowing me to choose which side gets the negative sign for the change and which side gets to be the positive side. Let's begin our discussion about reaction quotients by not thinking about any specific reaction, but rather about a generic reaction. Just one in which reactants are in equilibrium with products. Now, we know that the equilibrium constant expression for any equilibrium at all will be some function of products divided by some function of reactants. Essentially, their concentrations multiplied or raised to a power equal to their coefficients. But for now, let's not worry too much about that and just say products over reactants. Now, at equilibrium, we know exactly what these should be. But what if I were to use the equilibrium constant expression to describe a system that's not at equilibrium? And it wouldn't be the equilibrium constant anymore, would it? It would be something else, and we call that something else Q, or the reaction quotient. I can still put concentrations of products and reactants into this expression. They're just not necessarily equilibrium concentrations anymore. And this will give me a tool that I can use to predict how an equilibrium will shift, or how a system will shift to reach equilibrium. So think about this. Let's say that I have a system and I calculate Q and determine it's exactly equal to the equilibrium constant. What does that tell us about the system? Well, clearly, it tells us we're at equilibrium. This is going to be a very boring reaction because nothing's going to change. But if I put initial concentrations into this expression for Q and I find that it's actually less than the equilibrium constant, that tells me something very valuable. Think about what this means. If Q is smaller than KEQ, that means that its number is smaller. That means that its numerator is smaller, or its denominator is too large to be equal to K itself. So what will a chemical system do in order to rectify this problem and get Q equal to K? Well, of course, it's going to move to the right towards our products, bringing other concentration up, increasing the numerator, bringing reactant concentrations down, shrinking the denominator, until Q is equal to K again. So when Q is smaller than K, the equilibrium will shift to the right, towards products. Now, similarly, what if we have the opposite situation? What if we find that Q is greater than K? Our concentrations right now tell us that the number is too large when we put it into the equilibrium constant expression. Well, that would be a situation like this, in which products are too big, the numerator is too large. Reactants too small, the denominator is too tiny, creating a very large value for Q. What can our reaction do to remedy this problem? It can go backwards, right? This is an equilibrium. It can decrease products and increase reactants until we're back where we belong here at equilibrium. So Q gives us a valuable tool, this reaction quotient, in order to determine which direction a system will shift in order to reach equilibrium. So we can summarize the versatility, or we can summarize how we use Q based upon this little cheat sheet here that I've got for you. If Q is equal to K, we're at equilibrium, there is no shift. If Q is greater than K, the system will shift to the left towards whatever we've defined as the starting materials or reactants. And if Q is less than K, we expect the system to shift to the right, creating more of what we've defined as products and consuming more reactants. Let's put it to use really quickly and do one example. All right, I've got my cheat sheet handy and my question ready to go. When 2 moles of hydrogen and 2 moles of iodine are mixed with 16 moles of hydrogen iodide in a 1-liter vessel at 430 degrees, how do we expect that system to behave? Which direction will it have to shift in order to reach equilibrium? In other words, do I expect HI to form? Do I expect HI to be consumed? Or do I expect nothing at all to happen? Well, I'm fortunate because I've already done all the work I need here. I've got my equilibrium constant expression and my equilibrium constant from my previous work. Now all I have to do is put my non-equilibrium values in to calculate Q and compare that to the values for K. In this case, we've got 2 moles per liter of H2, 2 moles per liter of I2, and 16 moles per liter of HI. This will allow me to calculate the reaction quotient for my system before equilibrium establishes itself. And I discover that a number is 64. Q is greater than K, and therefore the system is going to shift back toward what I have defined as the starting materials in order to reach equilibrium. In other words, we're going to lose some of this hydrogen iodide and create more hydrogen and iodine gas than we started with. So let's summarize what we've covered today. It all started when French chemist Claude Louis Berthollet tagged along with Napoleon to Egypt, where he observed familiar processes from his laboratory, with the very critical exception that they were running in reverse. Now, this led us to consider a few familiar processes in which the conversion of states takes place in both directions simultaneously, and at the same pace, and this leads to what we call a dynamic equilibrium. Next, we took that equilibrium concept and we applied it to chemical reactions, first considering homogeneous and heterogeneous equilibria. Homogeneous meaning that all reactants and products are of the same phase, and heterogeneous meaning that reactants and products are of different phases. We decided to stick to homogeneous equilibria for today, specifically investigating the equilibrium among hydrogen, iodine, and hydrogen iodide. We saw how equilibria can be mathematically modeled using an equilibrium constant expression, in which products appear in the numerator, starting materials appear in the denominator, and each is raised to a power equal to its coefficient in the balanced chemical reaction. We then calculated an equilibrium constant for the synthesis of HI from hydrogen and iodine. Our constant was somewhat large, indicating an equilibrium that favors products. Next, we explored how to use the equilibrium constant to predict the outcome of reactions before we ever try to run them in the lab. Unfortunately for us, things didn't look so rosy even after increasing our hydrogen gas concentration. Our yields weren't great. Then we took a moment to think about the effects of multiplying reactions and reversing them. We saw how multiplying or dividing reaction coefficients leads to an exponential modifier for KEQ, and how reversing a reaction means that we have to take the reciprocal of the original equilibrium constant. Finally, we considered the reaction quotient, a mathematical tool created by entering non-equilibrium concentrations into the equilibrium constant expression for a reaction. And next time, we're going to explore not only how to model equilibria as we have today, but how to use those models to devise new ways to manipulate equilibria. Le Chatelier's principle is our topic for next time.